Alright, hello calculus students. Today we're going to look at solids of revolution. So you should have already watched that 80s vintage video where about the first 20 minutes went over a few techniques for solids of revolution. So we're going to amp up what we've been doing in calculus from looking at the area between two curves, and we're going to take regions between two curves or just underneath one curve, and we're going to revolve them in various ways to create three-dimensional volumes. So that video is definitely something I might go back to if you want some extra examples of various techniques from chapter 7. There's three methods for solids of revolution. The third one mentioned in the video, which you didn't have to watch, was the shell method. The shell method I think is more abstract, so we're not going to be using it. The AP exam doesn't expect you to know it either. So what are the two other methods? See if you can think back. Pause the video and see if you can remember what those other two methods were. What you should come up with is the disk method and the washer method, where you subtract out a hole that's drilled through your region. So let's look at some examples of these two methods today. So first let's look at a parabola. Let's take that parabola and let's revolve it around the line y equals 1 and find the volume of the created solid. So just like always, in this unit especially, you first want to think about a picture and have a really nice picture drawn so you can physically think about the measurements and dimensions involved before you ever try to do any calculus. So I'm going to look at 2 minus x squared. And let's see, 1, 2, 1, 2. So that should be something like this. And it said this time take that and revolve it around the line y equals 1. So I'm also going to draw the line y equals 1, which is right here. Should probably label my edges. And it says to revolve it around that line. So they must obviously mean in this problem, this little region, I'll color it in blue a little bit, revolved vertically. So just like we did in 7.1, you want to always be careful and think about your infinitesimal rectangle. So my infinitesimal rectangle is going to go from the axis to the edge on every single problem. From the axis to the edge. And then I'm going to revolve that whichever way the axis. So clearly this is going to be a vertical revolution. And before you even start going into the calculus, or at this point, you definitely want to think about what this is going to look like as a shape three-dimensionally. That can also help. So I think we're going to get like a little football type shape up here, I think, for this one. So that's going to be the radius of my dx infinitesimal disk or washer. I don't think we have another radius here. These are just going to be disks that go like this. So this is an example of the disk method. Alright, so let's integrate. So we're going to integrate those disks or add them up between here and here. So we need to figure out where these intersections happen. It looks like about x equals 1 and negative 1. I'm not sure yet until I solve. So solve the system of equations. Where's y equals 1 intersect that curve? I'm going to substitute y equals 1 into the other equation because that's y. So 1 equals 2 minus x squared. Solve, subtract, subtract, divide by negative 1. Square root both sides and you get plus or minus 1, just like what it looked like from our picture. So we need to integrate from negative 1 to 1, and we need to think about the radius of the disk. So the radius of the disk we said was this. Don't let this part confuse you. Right here was the radius of our disk. So we're going to go, the volume is going to be pi r squared because that's the area of a circle, and we're going to have that times the thickness dx. So what is that going to be? Let's see, we can factor out pi since it's a constant, and we need to think about how long this is. So how long is that little radius there? I think it's going to be this long. So this long is how high the function is, or 2 minus x squared. So we need to go 2 minus x squared minus this part, which is fixed at 1. You always want to think about what's changing and what's fixed. This is changing as you go along the curve in that region. 1 is not changing at all. So the radius is going to have a subtraction in it, even though it's not the washer method. So we're going to have the function 2 minus x squared minus 1. squared dx. Solve your integral and you're done. So let's see, pi 2 minus 1 is 1. For integrating something like that, we know we want to expand it. We don't want to try to do something with a product rule because there is no such thing for integral. So first thing squared, this times 2 is minus 2x squared. That thing squared is x to the 4th dx. Continuing to integrate, I get pi, and let's see, so integrating 1 is x, integrating this is minus 2/3 x cubed, integrating this is x to the 5th over 5, from negative 1 to 1. Alright, pi. Using the second fundamental theorem of calculus, first part of the fundamental theorem of calculus. Anyway, sticking 1 in, 1 minus 2/3 plus 1/5. Sticking negative 1 in, negative 1, negative odd is negative, that's positive then. Sticking negative 1 in, negative. And we just need to simplify, so that's going to be pi 1 minus negative 1 is 2. Negative 2/3 minus 2/3 is minus 4/3. 1/5 minus 1/5 is 2/5. So that's going to be pi times, let's see, common denominator here would be 15ths. So that's 30 15ths times 5 minus 20 times 3 plus 6. So this is going to be pi times 10 plus 6 is 16 15ths. So this is 16 pi over 15 cubic units because we're doing volumes. Alright, let's look at another problem. Let's take that and now revolve it around the x-axis. So let's go back to the same shape and revolve it around the x-axis. If you guys want to hang out for a second, if you have questions, if you don't, you can leave. I've got to finish this video though.
Where do you want the rocket?
Oh, just leave it there, I'll take care of it.
Okay. Yeah, see, Mr. Good.
Take it easy.
I'm good.
You guys didn't have calculus problems you wanted to look at for Calc 2?
I think I got them.
Okay, if you got them, just give it to me right there.
They're not in my work as being gotten, but I thought about it.
Next question. Are we friends on Steam or something? Because I don't know how you would know that I was playing Dungeons and Dragons.
Yeah,
We are? Who are you?
a guy.
It's probably Archimedes something. That's what his Xbox is.
Is it
Maybe.
Yeah, look at my Steam thing real quick.
Okay, so going back, we're going to take this solid of revolution and now we're going to revolve it around the x-axis. You guys have a good rest of your weekend.
Good job.
So this time we're going to take that region that's cut by y equals 1 and revolve it this way around the x-axis. So let's color it in again so we're clear. And it's going to then have basically another piece that looks kind of like that down here. So this time we've clearly got a hole that we need to subtract out. Sam, did you find what you needed to?
Yeah.
Okay. So we've got a hole that we need to subtract out. This time we're going to do the washer method. So we need to clearly write what our two radii are. So the top one is going to be from the axis, or the big R is always going to be from the axis out to the curve. So I'm going to go from the axis, which is the x-axis, out to the edge. That's big R. Colors are definitely helpful on these problems. And then my small radius, what I need to subtract out, is from the axis to the inside curve. That's pretty much the rule of thumb for every time. So there you go. So the outside axis is changing, and on this one the inside axis is fixed. So it's basically just a cylinder. You don't even need calculus, but let's just do it like that. So we're going to be going from the same edges, -1 to 1. And this time we're going to go pi big R squared minus pi little r squared dx. So we've got pi times the integral, and now we've just got to be real careful about obtaining those radius measurements. So big R is from here to here. That's just the function, isn't it? That's just the function that we called 2 minus x squared. I don't have it on there, but same one as last problem. So that's 2 minus x squared squared. Then we need to subtract out the little function. Well, it's fixed. It's just this high all the time, so it's just minus 1 squared dx. And that's it. So now I've just got to do that problem, and we'll have this volume. So we've got the volume, and then we just got to expand this out. So 4 minus 4x squared plus x to the fourth minus 1 dx. So that's going to be pi. 4 minus 1 is 3. So I've got pi, and I've got 3x minus 4/3 x cubed, integrating, of course, and x to the fifth over 5 from negative 1 to 1, so that's going to be pi, plugging 1 in, plugging negative 1 in. And it's a really similar algebraic computation from last time, it looks like. So this time we've got pi 3 minus negative 3 is 6. Negative 4/3 minus another 4/3 is minus 8/3. 1/5 minus another fifth is going to be plus 2/5. So that's pi times what? Let's simplify here. 15ths again, it looks like. So how many 15ths is that? 6 times 15. Tired. Should be able to do that. I'm not going to even try. That's 90. Duh. How many 15ths is this? Times 5 times 5. 8 times 5 is 40. How many 15ths is this? 3 times 3. The same 6 15ths from the last problem. Oh, that's 90 15ths. Whoops. So now we've got 90 minus 40 is 50, plus 6 is 56 15ths. So there you go, there's your answer, 56 pi over 15. Remember, what are we working in dimensionally? Is volume, so units cubed. There's another problem. Let's look at a different base region and revolve it a couple different ways before we leave off for today. Let's consider the region between the square root of x and x squared. Really simple functions composing the edges of the region, but a different problem. So x squared looks like this, and this, of course, but I think we're really just interested in the part between it and the square root of x. So really just that portion of x squared, that side, is what we're concerned about today. So the region is this, shading it in a little bit, and let's revolve it a couple different ways. So first let's revolve it, problem A, let's revolve around the x-axis again. So here's the x-axis, of course. Let's do that revolution first. So remember the rule of thumb, from the axis to the outer edge if you're doing a washer method. Oh, you should probably think about this first. If we want to revolve this around, won't it kind of look like this? That's the kind of shape you're going to get. So think about, do you need to subtract something out or not? I think the answer is yes. If you're having a hard time seeing that this is the washer method, just ask yourself, are there two edges to your curve? If there's two edges, that's two radiuses. If there's one edge, that's one radius. Sometimes there'll be a subtraction in just the one edge, but if there's two edges, it should probably be the washer method. So to the outside edge from the axis, it's from here to here. There's big R. The place we'll be subtracting out is from the axis to the inside edge. There is small r. You can clearly see those two radiuses. Okay, so the volume is going to be, where do these intersect? Oh, we need to solve that problem first. So a little scratch work. X squared equals root x. How do we solve this? Should I square both sides? Yes. So that's x to the fourth equals x. So where is that equal? It's going to be x to the fourth minus x equals 0. That's x. You can factor that. X is shared, x cubed minus 1. So they're equal to each other at x equals 0, and if you put 1 there, you'll get x equals 1. The other roots to x cubed minus 1 are imaginary. If you remember that, you could factor this, in fact, with difference of cubes. We don't need to. This is clearly just happening at x equals 1. Okay. So now we've got our edges for our integration. We're going to go from 0 to 1. Washer method. Pi big R squared minus pi little r squared. This is getting distributed, of course. Okay, so 0 to positive 1. Alright, so now the most important part of the process, figuring out what the radiuses are from our picture. If you have a nice picture, it shouldn't be very hard. Big R, I think, is clearly just the height of the square root function. So it's the square root of x being squared. Little r is this distance, so that's just the height of the x squared function. So it's x squared being squared. There you go. That's our integral. Find the volume. So integrating, well, I'm simplifying first, I should say. Square root cancels squared, or squared cancels square root, x. That's x to the fourth dx. Let's see, so we get pi times, now I'm going to integrate. That's x squared over 2. The antiderivative of this is x to the fifth over 5. From 0 to 1 evaluated. So pi times, plugging 1 in, that's going to be a half, plugging 1 in, that's a fifth. Here's my fundamental theorem part 1, plugging 0 in, I'm just going to get 0 for both. So that's going to be pi times a half minus a fifth, which is going to be pi times, make a common denominator however you want. Let's see, tenths, 5 tenths minus 2 tenths is 3 tenths. So this is 3 pi over 10 units cubed because we're doing volumes again. Alright, so for the last one for this video, let's think about that same region, but let's revolve it a different way. So this is what we got when we revolved it around the x-axis. For part B, let's revolve the same region around the line x equals negative 1. I'm kind of doing these revolutions arbitrarily just to show you a variety of things you could do that would work for different things for your project and just common problems. So I don't think the radius and stuff is going to stay the same, so let me erase that and kind of clean up the picture. So same base region, different revolution, it's going to mean different radius. So here we go. There, that picture is pretty clean now. So where is the line x equals negative 1? That's vertical, of course. So that's going to be like over here. Oh, let's look at this actually. Scale, there's where I put that as 1. Let's say over here then. There we go. So we want to revolve it this way. These discs or washers, we have to think about that, are going to be clearly horizontal. So this is our first problem of that type. And we're going to have like this much space, so then it's going to be like right here, and then it's going to be like this kind of thing. So you can imagine this kind of bowl with a big giant hole cut out of the bottom. So, what do you think? Discs or washers? Think from the axis, there's one curve edge, and from the axis there's another curve edge. So I think we have washers again. So our volume this time is going to be based on those. So let's draw those in. So we've got the big one is to the outside curve, and the small one is to the inside curve. Okay? So I think our strategy is mostly the same. We're going to have big R squared minus little r squared. The big difference here is it's not dx. This is clearly dy. Those are clearly y infinitesimal rectangles and y discs. If if you made them into disks by drawing the big circle. Okay, so are we going to go from x's here or from y? If this is y, these better be y. So we better make sure. This is clearly y equals 0. We said that they intersect at x equals 1. If you plug 1 into that, don't you get 1? If you plug 1 into that, don't you get 1? So it is 0 and 1 still, but that's just coincidence on this problem. A lot of problems are not going to be like that. I'm going to label those as y, just so you're clear. And now probably the most challenging part is figuring out the radiuses, just like last time, the most challenging and the most important. So the big R is going from that all the way out to x squared. But we can't be putting x stuff in here. It's got to be y stuff. There's your clue in the notation. Go by the notation. Leibniz made it that way for a reason. So it's from here to here that measures the x coordinate on the curve. Remember, we're working with y equals x squared for this one. Y equals x squared. So if you solve for x and square root both sides, you get x equals the square root of y, plus or minus, but we're just using this one, right? Okay, so that's x equals the square root of y. That, let me get a new color here, brown perhaps, is just from the origin out to there. For big R, that's clearly not all of big R. That's going to change. It's going to go from smaller and then bigger and bigger and bigger x values all the way out to the intersection. What's not going to change is this part. For all of that, it's always going to be fixed at whatever this length is, which is 1. So big R over here is going to be the square root of y, and then you've also got to add this 1 in, plus 1, and that's getting squared. Now let's do small r. I think it's going to be really similar. Oh, excuse me, minus. We're cutting that whole out. So small r, we're going to go from here to here, and then we've also got to add that 1. So small r was based on the curve, I'll do it in green, it's going out to this curve, the square root of x. So there we've got y equals the square root of x. So we've got to solve for x by squaring both sides. So that says x equals y squared. That x is this distance x, and then we've got to add on the 1. So we're here, we're going to have y squared plus 1. And that's going to be the volume of this strange pot without a bottom. Obviously water's just going to flow out, but right there. Let's finish up and do this integral now. So the volume's going to be integral from 0 to 1. Squaring this, I get first thing squared, 2 times the cross terms, second thing squared, it's pretty boring, minus first thing squared, 2 times the cross terms, last thing squared, dy. I'm going to simplify my like terms, any that I have. I have a negative y to the 4th, check. Let's see, I have a negative 2y squared, making sure to distribute this. 1 minus 1, these go away. Let's see, I also have a plain old y right there. And I also have a 2 root y, dy. Right, I'm going to erase some of this to get some space. So the volume is equal to the integral. Now let's just start integrating. So integrating negative y to the 4th, we've done that one a whole bunch of times in this video. We've also done this one a bunch of times. Y is y squared over 2, the antiderivative. And if you remember this, you're supposed to go 1/2, so I go y to the 3/2, 2/3. From 0 to 1. Thank goodness that's a 0, because these are all going to go away. So that's going to be, plugging in 1, I get negative 1/5. Plugging in 1, that's negative 2/3, plus 1/2, plus 2/3, because 1 to any power is 1. And 0 going in all these spots is going to be 0 everywhere, so it's just minus 0. All right, common denominator, 5, 2, 3. Let's see, 2 and 3 go into 6, 30. So 30ths. What do we have here for 30ths? This is times 6, that's negative 6 30ths. This is times 15. So that's minus 15 30ths times, what is 30? Times 15 plus 15 30ths. I guess I should have canceled those, oh well. times 10, that's plus 10 thirtieths. So what do we get here? We get equals chop chop, 10 minus 6 is 4 thirtieths. And I forgot something kind of important the whole time. See if you can spot it. This problem is disks with area of pi r squared. So shouldn't I have had a pi out in front the whole time here? Etc., times pi. So it's 4 pi over 30 units cubed. That's our first set of examples on solids of revolution. Hope you liked them. I'll see you next time.